So let's talk about the space shuttle. I mean, this thing wasn't just a rocket, and it wasn't just a plane. It was, and you could easily argue this, the most complex machine humans have ever built. For 30 years, this was our ride to low Earth orbit, a reusable spaceplane that could land like a glider. But the question is, how in the world did it actually work? We're going to break down the entire journey, from the pad all the way back to the runway.
Okay, so before we get into the nuts and bolts, you've got to understand the stakes. That quote you see? That's from astronaut Bruce Milnick. He's talking about his very first mission, STS-49. Their job was to go up there and rescue a satellite worth millions and millions of dollars that was just stuck in a totally useless orbit. I mean, talk about high stakes, high risk. This mission pushed the brand new shuttle, Endeavour, to its absolute limits, and it all started with the most violent, chaotic part of any trip to space, the launch.
Yeah, getting a 2,000-ton vehicle into orbit, it's not exactly a gentle process. It's really just a controlled explosion. It's this whole sequence of unbelievably powerful, but also super precise events that all have to go off perfectly, and I mean perfectly, in the blink of an eye.
So let's look at those final moments before launch. It's just this incredibly fast sequence of events. At T-minus 10 seconds, these little sparklers fire off to burn away any stray hydrogen gas. Super dangerous stuff. Then, just 3 seconds later at T-minus 7, the three main engines roar to life, just chugging fuel from that giant orange tank. By T-minus 3, they're already at almost full power. But get this, the shuttle is still bolted to the launch pad. And then, at T0, everything changes. So here's a wild thing. The main engines, they aren't perfectly centered on the stack. So when they fire up, their insane thrust literally bends the whole shuttle stack forward. The entire thing, the orbiter, the tank, the boosters, it lurches over and then springs back. And you know what the NASA engineers call this? In a moment of pure technical genius, they called it the twang. Can you believe that? The whole system is under this incredible stress, and it's held to the ground by just 8 explosive bolts.
Okay, so right as that twang is happening, the command goes out, light the solid rocket boosters, the SRBs. And folks, this is it. This is the point of no return. A safety pin gets pulled, a device arms itself, and then a detonator fires what's basically a small rocket inside the big rocket. This ignites the entire column of solid fuel all at once. At the exact same microsecond, those explosive nuts on the hold-down bolts just vaporize. There is no off switch, there's no turning back.
And the power we're talking about here, it's just staggering. Let's try to put this into perspective. Each one of those SRBs produced 13,000 kilonewtons of thrust. You know what that is? That's almost double the thrust of an entire Falcon 9 first stage from each booster. These were, hands down, the most powerful solid rockets ever used for human spaceflight. And together, they provided over 70% of the total thrust at liftoff. Just incredible.
So the bolts are gone, the shuttle is free. In the next 2 minutes, it's just a brutal, violent, shaking ride straight up, fighting against gravity and punching through the thickest part of our atmosphere.
But wait, this brings up a huge question, right? How do you control the thrust of a solid rocket? I mean, you light it and it just burns. You can't turn it off. Well, the engineers came up with a truly genius solution. Instead of just a hollow tube of fuel, they cast the solid fuel in the shape of an 11-point star. Now, why would they do that? Well, that star shape gives you a massive surface area at ignition for maximum thrust right off the pad. But then, as those points burn away, the surface area gets smaller and the thrust naturally decreases. It was a brilliant way to keep the shuttle from literally ripping itself apart as it got lighter and faster.
Now try to imagine what it's like to be inside this thing. For the first 45 seconds, it's just a deafening, bone-shaking roar from the rockets. Then you go supersonic. And just like that, you've outrun your own sound. The roar just vanishes. And as astronaut Melnick described it, it's replaced by this howling sound of air just screaming past the hull. He said it was like a train howling through a tunnel. Wow.
Okay, so about 2 minutes into the flight, the SRBs are out of gas. It's time to ditch them. And for a rookie astronaut like Bruce Melnick, the moment of separation was, well, it was utterly terrifying. He described it as this big bang, and then suddenly you're inside a fireball. His first thought was, geez, dude, we just blow up? I mean, it's this incredibly shocking, violent event that feels like a complete catastrophe.
But here's the thing. What felt like an explosion from the inside was, in reality, just another perfectly choreographed dance of engineering. The booster nozzles swing into a neutral position. A series of explosive bolts fire to cut the connections, and then 8 small solid rocket motors on each booster fire,
pushing them cleanly away from the shuttle so there's no chance of a collision. All in a split second. All right, so the boosters are gone. For the next 6.5 minutes, the shuttle is flying on just its 3 main engines. They're still drinking up all that liquid hydrogen and oxygen from that giant, iconic orange tank. Now, that tank was more than just a fuel tank. It was the structural backbone of the whole system, connecting the orbiter to the boosters. And it was also the only major part of the whole shuttle program that wasn't reused. It was designed to just break apart and burn up in the atmosphere on re-entry.
So the mission's done, they're in space, everything's great. But now comes what many considered the most dangerous part of the entire mission, coming home. The shuttle had to go from being a spacecraft in a vacuum to a 100-ton glider with no engines, smashing into the atmosphere at almost 30 times the speed of sound, a fiery re-entry. You see, at those kinds of speeds, air doesn't really act like air anymore. It becomes a superheated plasma. We're talking about temperatures on the surface of the shuttle, especially on the nose and the edges of the wings, hitting over 1650 degrees Celsius. To put that into perspective, that is hotter than molten lava. Meanwhile, the aluminum structure of the shuttle underneath, that would melt at just 177 degrees. So you have a huge problem to solve. And the way they solve this heat problem is completely counterintuitive. You'd think, okay, you need a sharp, pointy nose to cut through the air, right? But that's actually the worst thing you could do. A sharp nose would attach the shock wave right to the skin of the vehicle, basically cooking it. Instead, the shuttle used a blunt body design. It's weird, but what this does is it creates a shock wave that's detached, that stands off from the body, leaving a cushion of insulating air between the shuttle and the hottest part of that plasma. It's not as sleek, but that design was literally the key to survival. So to handle all that insane heat, the shuttle was covered in this incredible patchwork of different materials. You had the reinforced carbon-carbon on the absolute hottest parts, like the nose cap and the wing edges. Then you had the famous black silica tiles all over the belly of the orbiter. On top, where it didn't hear as hot, they used white tiles, mainly to reflect the sun's heat when they were in orbit. And then other, less critical areas were covered with these flexible insulating blankets. But the real secret to those tiles is just mind-blowing. If you asked what they were made of, the answer is mostly nothing. Seriously. 90% of a tile's volume was just air, empty space. The other 10% was this delicate matrix of pure silica fibers. This meant they were incredibly lightweight and just phenomenal insulators. There are famous videos of engineers heating one side of a tile until it's glowing red hot and then immediately picking it up by the corners with their bare hands. Just amazing. Now, during the absolute hottest part of re-entry, for about 12 long, agonizing minutes, that cloud of plasma around the shuttle got so dense that it blocked all radio signals. This was the infamous communications blackout. Back in mission control, all they could do was wait. Just sit there and hope that the onboard computers and the crew were flying the vehicle through that inferno correctly, because they were completely, utterly on their own. Once they finally came out the other side of that blackout, the shuttle wasn't a spacecraft anymore. It was a glider. But it wasn't a graceful, sleek glider. Nope. The astronauts themselves called it the flying brick. And here's the kicker. It had exactly one shot to make it to the runway. One chance. There were no engines, so there were absolutely no go-arounds. And the physics of flying at these hypersonic speeds are just weird. The air gets so compressed in front of the control surfaces that they actually start to work backwards. So if a pilot wanted to bank the shuttle to the left, they'd actually have to input the command for a right bank. Now, of course, the onboard computers handled all of that translation automatically, but it just goes to show you what an incredibly alien environment they were flying in. So, to get rid of all that speed and altitude, the shuttle basically fell more than it flew. Its final approach was this terrifyingly steep 20-degree dive. To give you some context, that is nearly 7 times steeper than the final approach of a normal commercial jetliner. The whole point was to just bleed off a ton of energy in a controlled dive right at the runway. And then, in one of the most critical moments of the whole flight, technology actually took a backseat to a good old-fashioned human. The landing gear wasn't automatic, and you might wonder, why not? Well, the engineers were worried that a stray cosmic ray could hit the computer in orbit, accidentally trigger the gear to deploy, and there would be no way to pull it back up. That would be a complete disaster. So the final command to lower the wheels, it was always manual. Just a switch, flipped by the pilot's hand. Okay, so after touching down on the runway at over 360 kilometers per hour, the shuttle needed some serious stopping power. That's where the drag chute came in. And this is really cool, because this is where our whole story comes full circle. That drag chute system, it was used for the very first time on the maiden flight of the Shuttle Endeavour, the exact same STS-49 rescue mission that astronaut Bruce Melnick was telling us about, right back at the beginning. Look, there's no denying it. The Space Shuttle was an absolute triumph of engineering. A machine that could launch like a rocket and land like a plane. It was incredible. But all of that immense complexity also made it really expensive and, as we know, sometimes tragically dangerous. It absolutely pushed the boundaries of what we thought was possible. But it leaves us with this big, powerful question. As we look to the future of spaceflight, was this marvel of complexity the right path forward, or was it a brilliant but maybe an ultimately unsustainable detour?